Today, let's begin with a single question. How long is Britain's coastline? It sounds like a question one line in an encyclopedia could settle. Surely somewhere a single correct number is written down. It seems no different from asking how many kilometers it is from London to Edinburgh. But astonishingly, this question has no single fixed answer. Or rather, it has infinitely many answers. The more precisely you measure, the longer the coastline grows, and that growth never stops. Sounds like wordplay, doesn't it? Whether you use a meter stick or a tape measure, a desk stays 1.2 meters. Measure the same coast with nothing but a different ruler, and the answer split apart 0.9, then 1.2, then 1.89. So why is it only a coastline that changes every time you measure it? This has a name: the coastline paradox. Follow this paradox all the way down and you meet a strange idea: fractal dimension. So let's head out to the shore. The story begins in an unexpected place. On the desk of a man who studied war. That man was Lewis Fry Richardson, a British mathematician and meteorologist of the early 20th century. He set out to answer one enormous question with numbers: why do nations go to war? And he formed a hypothesis: the longer the border two countries share, the more they might find to fight over. So he looked up the border lengths of many countries in encyclopedias and began copying them into a table. But as he filled in the table, he noticed something odd. The very same border had two different lengths. Spain recorded this border as 987 kilometers, while Portugal wrote down 1214 kilometers. The Netherlands put its border with Belgium at 380 kilometers, and Belgium called it 449 kilometers. It is the same line, yet one side is longer by roughly 20%. So who got it wrong? Astonishingly, nobody was wrong. The two countries had simply measured with different rulers. The smaller the country, the more carefully it measured with a shorter ruler, and shorter rulers gave longer lengths. The length was never a property of the border itself. It was a number that depended on which ruler you measured with. It looked so trivial that it was written down as little more than a footnote, and that one line would open up a whole new kind of mathematics. Now it is our turn to look closely at what Richardson had actually seen. Measuring a coastline is really the same as walking along it, one step of the dividers at a time. You open the dividers to some fixed width, then move along the coast one step and another step. Multiply that number of steps by the length of the ruler, and that is the measured length of the coastline. Here is the key point: the two legs of the dividers are always joined by a straight line. So when the ruler is large, every small bay and headland that falls inside a single step simply gets skipped. Shrink the ruler and it squeezes into the bay, following every fold inside it. And here is the problem: a coastline holds folds of every size without a single one missing. Zoom in and you find another coastline. Bays inside bays, and inside those inlets and rocks again. So every time you shorten the ruler, new folds keep appearing that you simply could not see before. Now let's measure one imaginary coast with three rulers of different sizes. We start with the largest. Shorten the ruler further, and the number of steps jumps from 3 all the way to 10. Shrink it once more, and the steps climb to 42, while the length swells to 1.89. One coast for rulers for different answers. The smaller the ruler, the bigger the answer. None of this would ever happen with a desk. The length of a desk settles down and converges to one value. But with a coastline, the shorter the ruler, the more the length grows, and it never stops. Let's write that difference in a single line. Call the ruler length epsilon and the measured length L. L is roughly F times epsilon to the power 1 minus d. Do not let it scare you, just keep your eye on d. For a smooth line like the edge of a desk, a circle, a straight line, d is 1. The exponent becomes 0. So whatever epsilon may be, the measured length always stays pinned to the constant f. But for a coastline, d is greater than 1, and that flips the exponent straight into the negatives. So as the ruler shrinks toward 0, the measured length never settles down. It just keeps on growing. This mysterious number d is the real protagonist of our story. In a moment we'll reveal what it is. Every coastline looks different each time you see it, and going out with a ruler to measure one is no small chore. So mathematicians built themselves a toy coastline, one that distills a single property cleanly, length that grows without end. In 1904, the Swedish mathematician Helge von Koch devised exactly that, the Koch curve. The recipe is simple enough for a child to follow. Just 3 rules. Cut the segment into thirds, take out the middle piece, and fit 2 sides of a small triangle into the gap. One segment becomes 4, and the total length grows by exactly 4/3. Then the same rule again on each of the 4 new segments. After just 3 stages, the length has already more than doubled. And again forever. After n stages, the length is 4/3 to the nth power. Join 3 Koch curves into a triangle and you get the Koch snowflake. The snowflake's perimeter does exactly the same. Every single stage it grows by a factor of 4/3. Plot that perimeter on a log axis, and it climbs in a straight line with no sign at all of stopping. So repeat forever, and the perimeter diverges to infinity. But here comes the twist. And yet the whole snowflake fits neatly inside a single circle, which means its area is finite. It fits on a scrap of paper no bigger than your palm, and yet its border is infinitely long. A field the size of your palm, ringed by a fence of endless length. Hard to picture but true. This is the purest mathematical version of the trick the coastline played on us. Faced with a curve whose length runs off to infinity, what on earth should we be asking? Now for the climax of the story. One mathematician changes the question itself. In 1967, Benoit Mandelbrot digs Richardson's footnote back out. His answer was shocking. Asking how long a coastline is, he said, is itself the wrong question. A coastline holds another number, one that never changes, in place of a length that shifts every time you measure it. That d we hinted at in Chapter 2. In epsilon to the power 1 minus d, the d sitting in the exponent is the fractal dimension. The way to find that dimension was already sitting in the very table Richardson had passed over without a second thought. Take the lengths measured with rulers of many sizes, and lay both axes down on a logarithmic scale. And then the points fall into place, lining up along a single straight line as if by magic. And the slope of that line is exactly 1 minus d. Read the slope and out comes the dimension. This picture is named after Richardson himself. We call it the Richardson plot. The smoother the line, the closer the slope is to 0, and the closer the dimension d gets to 1. The more jagged the coast, on the other hand, the steeper and more negative the slope becomes, and d grows larger than 1. Run the code from the original article just as it is, and the difference between the 2 curves prints out in hard numbers. The smooth arc gives d equal to 1.009. The torn-up coast, 1.378. Roughness has turned straight into a number. Line up the values measured on real coastlines, and the differences are startlingly clear. The relatively smooth coast of South Africa comes in at roughly 1.05, while Britain's west coast reads 1.25. And Norway's coast, shredded by fjords, climbs all the way to 1.52. And then our little toy, the Koch curve. Its dimension is log 4 over log 3. The Koch curve is 4 copies of itself, each one 1/3 the size, so 3 to the power d equals 4. That value is about 1.262, a number that almost overlaps with the 1.25 of Britain's west coast. A dimension of 1.25. That means it is neither a one-dimensional line nor a two-dimensional surface, but somewhere in between. A dimension that isn't a whole number. This was the door Mandelbrot opened onto a new geometry. Fractals. Only one thing is left, to lay a ruler on the coast with our own hands and see whether it's really true. Now it's time to see it with our own eyes. We'll measure the same coastline 4 times, shrinking only the ruler. This whole long story comes down in the end to a single sentence. Shrink the ruler, and the coastline grows longer. Here is the first pass. The yellow dots are where the dividers landed. The red line is 1 step. 7 steps and the length is 1.12. Now cut the ruler in half. The steps climb to 21, and the length jumps to 1.68. Have it once more and the steps become 50, with the measured length reaching 2.00. Shrink the ruler further and the steps run to 226, with the length soaring all the way to 2.71. Put the 4 passes side by side. The shorter the ruler, the more new bends come into view, and the length grows again. As the ruler length epsilon goes to 0, L of epsilon diverges to infinity. There is no value it settles on. So an exact length for a coastline was something that never existed in the first place. Now let's go back and stand in front of that very first question again. How long is the coast of Britain? Now we know. This question has no single answer. Or to put it more precisely, the question itself was wrongly posed. What we should ask a coastline is not how long it is, but how rough it is. Smooth South Africa and torn Norway. What separated the two was a dimension of 1.05 versus 1.52. A single footnote from Richardson, written while he was hunting for the causes of war, became fractal geometry in Mandelbrot's hands. Look at the world through this lens, and coastlines are not the only things that grow longer the finer your ruler gets. The outline of a cloud, the ridge of a mountain range, the forks of lightning, the branches of a tree, even the airways and blood vessels inside our lungs. Nature was never straight lines and circles. It was an endlessly rough fractal, written in dimensions that are not whole numbers. One question that looked like the simplest of all threw open an entire era of mathematics. Next time you stand at the shore, remember that the coastline beneath your feet is, in truth, infinitely long. And remember, too, the one tidy number hidden inside that infinity, the dimension d. If you enjoyed today's video, please subscribe, hit like, and turn on notifications. See you in the next story.